Welcome to Unit 2 review of basic algebra. Similar kind of approach to Unit 2 is what we did for Unit 1. Unit 1, we just did a quick overview, went through a few things. The idea being it's more diagnostic than instructional. What we're trying to do here is focus on those things that you would have normally taken in a previous math class and see how much of that did you retain, how comfortable are you with the material, that kind of approach. Okay, so it's not meant to cover everything, although the textbook does a pretty decent job of approaching this topic matter. Okay, so as we go and as we discuss this and as we try some practice problems, the thinking here is that we're trying to expose any kind of gaps in your knowledge. This basic algebra is going to be very, very important when we start to deal with future topics, especially linear algebra. Okay? So any kind of problems that you may have with this topic, we want to get that dealt with right away before it becomes a really, really, really big problem in the linear algebra unit. Okay. So it starts off like most math chapters do, a little bit of terminology. So an expression containing one term is called a monomial. If it's got two terms, it's a binomial. Three terms, it's a trinomial. Anything more than one term, we just call it a polynomial. And you'll see the word polynomial more than anything else. When you go to add and subtract these items, only like terms can be added and subtracted, right? So A's added with other A's, B's added with other B's. So 3A plus 2B is 5B's. 5A minus 1B is 4B. Okay, that kind of thinking. No different than the approach you took way, way back when you were just a wee little one, probably even before school. Started, and you sort of knew if you had 3 candies and you ate 2 candies, you had 1 candy left over, right? You have 1 candy. Doesn't say anything about what happened with bananas or rocks or sticks or pencils or pens or batteries. Doesn't matter, right? You just took your candies, you ate the 2 candies, you had 1 candy left over, right? So you were adding, subtracting like terms even way back then. Now, we do it in algebra. It's no different. So all this stuff, we all know how to do it. We've been doing it for as long as we can remember. Slap a couple A's and B's and W's in there, and somehow we start to think that it's something really, really different. And it's not. It really isn't. Okay, so there's some aspects here with multiplying and dividing with these monomials and polynomials. So if you're going to multiply 2 polynomials or 3 polynomials or whatever number, right? The key thing is just to be multiplying every term of the polynomial by the other polynomial or by the monomial, okay? So you would have seen this, if you had 2a plus 3b in brackets multiplied by a plus b, which the a plus b is in brackets, and just you did that expanding out so that you had a bunch of individual terms and you got rid of all the brackets. So this is really what approaches that, and that is somewhat important, and so you want to sort of get a familiarity with that. Okay, so if that's something that's kind of fuzzy, again, look at the review materials and start to play around with that a little bit. Division we're not going to do so much of, so it's there. It doesn't hurt to take a look at it, but it's not something that's going to really appear in this course. Not something that appears too terribly much unless you want to start taking a calculus. Then knowing how to divide like this, very, very important, because reducing that algebraic expression in order to take a derivative or take an integral of it does make your life very, very, very less stressful. Okay. So we have a couple of rules for exponents and rules for logarithms, and these are somewhat important, not just in this particular course, But if you happen to take economics or statistics, they're very important in that regard as well. So first thing is just dealing with exponents. So if I have an exponent, I have a number, a to the power. That power just means, the exponent, n. Okay? A is called the base, which makes sense. It's at the bottom of the number if you want to look at it that way. N is called the exponent. It's the little number at the top right. And so there's our basis for our number. Okay? We have a couple of rules for exponents, and these are very, very important. Notice the common bases here. Okay, so A is the same. And we're multiplying numbers with a common base, but maybe the same exponent, maybe different exponents, right? And that just simply retains the base, but with the exponents added to each other. Okay. Same kind of idea when you're dividing numbers with common bases and to have an exponent. It's like subtracting the exponents, but again, keeping the common base. Okay, so rule 1, rule 2, very related to each other. We have another situation where we have a base to power of exponent, and then that whole number is then to another exponent, and that's the same as multiplying exponents. Okay, so it's like a to the m. So we had a to the 3, let's say, right? A to the power of 3, that's a times a times a. And so if we had a to the m times 3, that's like a to the m times a to the m times a to the m. Well, I've got 3 m's there, right? What was my n in this case? It was 3, right? So again, 3 times whatever the inside the brackets exponent was. So fairly straightforward if you were to break that down. And then what happens when we have two bases with a common exponent? We can then expand that, and each base has that exponent. So a to the b in brackets to the power of n is the same as a with the exponent n, b with the exponent n. Same kind of idea with a divided by b to the power of an exponent, in this case n. It's like the same as a to the n divided by b to the n. So very similar approach with rules 4 and 5 as we had with rules 1 and 2. So kind of important to keep that in mind. Some basic sort of rules of it. The two ones that'll be most important. A to the 0 is 1, and you will see that maybe not in this course so much, but it does appear from time to time in other math related courses. A to where the power is a negative number, that's like 1 divided by a to where the exponent is a positive number. You will see this when we start to deal with compound interest, and we're dealing with present values and future values. And there's two approaches that you can work with this. You can just have a negative exponent, or you can have 1 divided by the same base with a positive exponent. The roots we don't do so much here. Those rules are there. Doesn't hurt to kind of have a good grasp of that, but not directly related, or doesn't really come up in this particular course. Logarithms, again, I don't want to tune you out because it's not in this particular class, but logarithms do appear again when you start to deal with topics such as linear regression. I mean, it can mathematically be used to derive certain values when we start dealing with the annuities. And it can be quite useful if we have a compound interest problem and we're solving for an exponent, and it's really tricky when the exponent is a variable. It's how do you deal with it up there? You can't get at it. I can't reach it. It's in the exponent. Get it down here. How do I get it down here? Down here being where all the other numbers are. Logarithms, very useful. Okay, so a couple of just basics of logarithm, and then build it up to the most important one, at least for this course, and possibly for when you take linear regression. So log this is natural log. It's the more common one. I'm an economist by trade, so as an economist, we love these natural logarithms. So I'm kind of natural log based, biased, or rather than, let's say, log base 10 or something like that. But the fundamental rules work the same. So if I have a natural log and then in brackets a and b, that's like adding the individual logarithms. Okay? And if I'm dividing within that logarithm operator, it's like subtracting individual logarithms. Now, we built up there's an exponent. I want to solve for the exponent. How do I get the exponent down here so I can work with it? Natural logarithms. So the log of a is the base, to the power of k. That exponent comes down in front of the logarithm operator. So it's k, just like a regular number, and then logarithm or natural logarithm of a. Now this makes that k much easier to solve, and off we go. A couple of more terms here that's more important, just in case you see the wording in reference materials. A root, sometimes they say, well, we're going to solve for the root. Root is just another way of saying, you're going to solve for the solution. So one variable has one root. Again, just a way of saying it's got one solution. Okay. We have a couple of conventions that we use to approach the problem, and we like to set it up so that we have variables on one side, numbers on the other side. Okay. Just that kind of basic kind of thinking. And we talked about in Unit 1, how do I approach that and how do I solve from that point forward. Okay, so a couple of things here just to wrap it up. Then we'll do some problem solving. Calculating rate of change. And these are just f, v with a subscript f just means that's the final value. A v, little subscript I, that's just the initial value. So we look at an ending value versus a beginning value. And we can see this in lots of contexts when we start talking about growth, whether it's growth in sales, growth in profits, growth in my portfolio, anywhere there's growth. It's all divided by the initial value, and then commonly we express it as a percentage so that we're used to dealing with percentages. A proportion would be perfectly fine, and a lot of people prefer to keep it in a proportion. But when you're trying to communicate it to a general audience dealing with percentages of change, it's just far cleaner and far easier, and usually your client will find it far more relatable, right? We've dealt with, as people, we've dealt with percentages for quite a while, and which is a certain comfort level there. Okay, and because we're in a business field, communication is very, very important to us. That we can communicate this to our client base is extremely important. Much easier to do that with percentages. Okay, here is the most important part of this whole unit that's going to carry forward for us throughout the entire course. How do I solve a word problem? Right? Because we are going to do that a lot. And that is sometimes the hardest thing in mathematics, is the word problem. Okay? So, first thing we do, it's 4 steps. Introduce the variable. We need to know what it is that we don't know that we want to figure out. So we need to know the variable. There is no way we can take a mathematical relationship expressed in words and translate that into an expression, a mathematical expression, unless I know what my variable is. What is it that I want to know that I don't already know? That is the most important step. Then we're going to take the information. So in words, we'll see a relationship, and all we will do is we'll translate that relationship that we see in words using the variable, and we just express that in a mathematical way, just using mathematical symbology. And so a couple of keywords that's mentioned here in this little document. Well, you're looking for more than. That's probably something addition, right? Less than. That's suggesting subtraction. Reduced by, half of. Ooh, that's kind of suggesting some sort of perhaps multiplication or division, right? Twice, 3 times as much. Those are suggesting multiplication. A third is big, right? Suggesting it's divided by a 3 or something like that, okay? So we're just going to be kind of very key. Reading comprehension, believe it or not, becomes very, very important to us here. Now we sort of see those key words in the original word problem. We have the variable. Now we're going to bring that all together and set up the algebraic expression or equation. Okay? Express it all completely in mathematical symbology and mathematical language. And then step 4 is we solve it. Right? And step 4, the actual math of it is often pretty straightforward. Once we get to step 4, for most of you, you're just rocking right through this. The big problems are that step 1 and step 2. And then, by extension, maybe a little step 3. Those are the hard ones. Those are the ones that cause the brain sweat. Okay, so let us go into some practice questions. Practice problems, and we are going to do a lot of word problems. And with every word problem, what do we start off with? We start off thinking, what is it that I want to know that I don't already know? Because that is our variable. That's step 1. Without that, nothing moves forward. I really need to figure out, what is it that I want to know that I don't already know? Okay, so we start off with first question, the book, The Intelligent Investor, by Benjamin Graham, a classic, written in the 30s, but an awesome book nevertheless. Some of it's become a little bit dated, but in one of the, I think the key lessons from that book, and it's in the first 100 pages of a very thick book, and that is that the biggest enemy of your portfolio is not your neighbor, it's not the Prime Minister of Canada, it's not the President of the United States, it's not the man in the moon, it is you. And so Benjamin Graham really had some intuition into the behavioral aspects of investing long before ideas of behavioral economics and behavioral finance have become popular or had become popular. Okay, so anyway, I digress. The book was on sale for 15% off its regular selling price of $31. What is the discounted price? Well, right there, it's telling me, what do I want to know that I don't already know? And question number 1, and that is the discounted price, which I will call D. Could have called it P as well. Call it whatever you like. Discounted price. So now I'm reading the relationship. And so I want to find that discounted price. And what does that equal to? Well, I start off with $31 because that's the undiscounted price. Okay, that's not terribly controversial. And it was on sale for 15% off. Off. Ooh, off. That sounds like subtraction. And then 15% off of what? That's got a kind of a multiplication vibe to it, right? So 0.15 or 15% of what? Off its original regular selling price of $31. There we go. We've taken the problem in words. We've determined what it is that I want to know that I don't already know, the discounted price, aka the variable. And then I've come up with a mathematical expression which we've translated it from the question into math. And now we just solve it. And the solving part's pretty simple, right? And we get the price of $26.35. There you go. That's it. No more complicated than that. No need to make it more complicated than that. Okay, let's now try question number 2. Okay. So a piece of hardwood flooring 75 meters long is cut into 2 pieces. Okay, so far not too bad. So the longer piece is 10 centimeters longer than twice the length of the shorter piece. Oh, man. Oh, gosh. Okay, what are the lengths of the two pieces? All right, so I'm thinking, whoa, what's this? 10 centimeters longer than twice the something or other? Anyway, so we take a step back. And we go, step one. What are the variables? What is it that we want to know that we don't already know? Look at the question. It says, what are the lengths of the two pieces? Two pieces. What are the two pieces? We have a longer piece. We have a shorter piece. Okay, so that's what I want to figure out. Those are my variables. L, we'll make that the length of the longer piece. And S, we'll make that the length of the shorter piece. Right? That's it. So now I have my two variables. Step one done. So now let's translate some of the mathematical speak that we see in this question. Right? Translate from English to math. So first step. A piece of hardwood flooring 75 meters long, cut into two pieces. We only have two pieces, longer piece and the shorter piece. Okay? So that means that that shorter piece plus that longer piece add up to the original 75 pieces of wood. Yeah, I know. Anybody who's ever cut anything knows that some of it goes to sawdust and blah, blah, blah. I get it. We're not going to deal with that. We're going to make it more complicated than we need to. We're not going to deal with the 1/8 of an inch or 1/16 of an inch, lost to the blade. But anyway, so the two pieces add up to 75 centimeters. Now we can get into the more complicated one. So the longer piece is, that sounds like L is, that's like an equal, 10 centimeters longer. That sounds like an addition to me. It's longer than, right? So I'm going to add that 10 centimeters to whatever I see next. Twice, that's a 2, the length of the shorter piece, which we'll call an S. Okay? I'm drawing the S a little funky so it doesn't look like a 5. Okay? But now we have our two equations, and we have two unknowns. This means we can find a unique solution. Okay? If we had one equation, we could only find a unique solution if there was only one unknown. We have two equations, two unknowns. It means we can find a unique equation, so a unique solution. So we're good there. We have two ways that we can deal with this. One way is we solve as a system of equations, which, hint, hint, we'll do in question number 3. But this way, because we're going to do it by substitution. Why? Because I've already got an expression that's kind of nicely set out that said that L is this. So L is L, right? Doesn't matter where we see it. One L is the same as the other L in sort of the mathematical, in this mathematical problem. So the L, which equals to the 2s plus 10, is the same as the L in the first equation. So I can substitute the 1L, which is 2s plus 10, into the first equation. And now I will reduce it to one equation and one unknown, which I know I can solve. So I get S plus 2S plus 10, and that equals 275. Gather up the like terms. Okay, so I have S plus 2S, one candy plus two candies. So I have 3S now, plus 10 equals 275. Subtract both sides by 10. 3s plus 10 minus 10 equals to 75 minus 10. 3s equals to 65. S equals to 21.67 centimeters. Okay, so I've solved the first one. Next step, I'm going to take that S, plug it into one of the two original equations, solve for L. Since we have an equation or an expression already set up for L, it's kind of easier just to use that one. So let's do that. We know that L equals 2 times S, 2 times 21.67, plus 10, and that L equals to 53.33 centimeters. Okay. If we want to do a double check, if we have time, we can just add those two numbers together. They should be equal to 75, the original length of the piece, which they do, and so we're all good here. Right? We're now able to move on to the next problem. Question number 3. Question number 3, we have an inventory of 2 types of caps. In inventory, we have a total of 100 caps valued at $2,480. If the Edmonton Oilers caps cost $22 each, well, the Las Vegas Golden Knights caps cost $26 each. How many of each cap were in inventory? Okay, starting off, what is it that we want to know that we don't already know? And that thing that we don't know that we want to know is the number of each cap in inventory. So let's make E equal to the number of Edmonton caps. L equal the number of Las Vegas caps. Okay. Hard part already done. Now, inventory was a total of 100 caps. So if I take the number of Edmonton caps, add it to the number of Las Vegas caps, those are the only 2 types of caps I have, those must add up to 100. Okay, so nothing controversial there, right? You have 100 caps, 2 types of caps. Each one of your variables represents the number of each one of those caps. So by adding them together, you're just basically counting up caps. The next thing is valued at $2,480. So I got $2,480 worth of caps. And it further tells me that the Edmonton caps cost $22 each, while the Las Vegas caps cost $26. So if I take the $22 for one single Edmonton cap, multiply it by the number of Edmonton caps, that represents my total amount, or my total cost, of Edmonton caps. I add to that the cost for one single Las Vegas cap multiplied by the number of Las Vegas caps, and I get the total cost of the Las Vegas caps. I mean, this is very important, because when we get to linear programming and we start talking about cost functions and profit functions, this is really what that is. Okay? So now I have my 2 equations. I have 2 unknowns, so I know that this is a solvable. I will get a unique solution. This is great. Well, we'll approach this one a little bit differently. So we're going to solve this one as a system of 2 linear equations. So my first equation will be the first one that we came up with. And my second equation will be the 22E plus the 26L equal to 2480, the cost equation. Now, we want to eliminate one of these variables. The logical one is, since this is being recorded in 2020, we'll eliminate the Oilers. Because why? Well, because the Oilers were eliminated before Las Vegas. Before Las Vegas, right now, as of recording, Las Vegas is playing the Chicago Blackhawks, so who knows what will happen. But Edmonton was definitely eliminated, so let's eliminate the Oilers here. So to do that, we want the coefficients in front of the 2 E's in the 2 equations to be the same. The easiest way to do that is I'm just going to multiply the first equation by 22. Okay? Now, I have to multiply everything in that equation by 22 in order to keep sort of the same relationship. Okay? So question number 1 is 22E plus 22L equals to 2200. This one's really easy to forget to do. And equation number 2 is 22e plus 26l equals to 2480. Okay. So now I have the coefficients in front of the e are the same, and they're both positive. So I'm going to subtract one equation from the other, and that'll cancel out the e, right? 22e minus 22e is 0e. Okay. Now, whether I go equation 1 minus equation 2 or equation 2 minus equation 1, that doesn't matter. It does not matter at all. It'll get you the same answer. Now, I'm going to go equation 2 minus equation 1 for no more complicated reason, as I want to end up with a positive number. It's just too much negativity in the world. Let's keep it positive, stay with the positive numbers, that kind of thing. Realistically, my biggest source of stupid mistakes is forget that negative sign. So if I don't have any negative signs, there's nothing for me to screw up. So let's go 22e minus 22e, and I get 0e, plus 26l minus 22l, that's 4l, and then 2480 minus 2200, that's 280. Okay, I can pretty much ignore the 0e, and I have 4l equals to 280. I divide both sides by 4, and I get L equals to 70. 70 Las Vegas caps. Cool. Now I'm going to take that result, put it into one of the other two equations. Now, E plus L equals 100. That's the easiest one to use, so I'm going to use that one. And so what do I get? I get E plus L, which is 70, equals to 100. And I'll take that 70, move it over to the other side. When I do that, it becomes a negative number. E equals to 100 minus 70, which is 30 caps. And I'm done. Finished. All tickety-boo, everything's wonderful. And I'm all set to go on to question number 4. Question number 4. Emera, a publicly traded Canadian multinational energy holding company based in Halifax, Nova Scotia. On May the 29th, 2020, its stock price closed at $55.10. At the end of trading on June 2nd, 2020, the stock price stood at $54.73. What was the percentage change in stock from May 29th to June the 2nd? All right. So we have a formula for that. Oh, what the heck was that formula? Let's go look back at our statistical toolbox, and we see that the change, which is C, is equal to the final value minus the original value, all divided by the beginning value, expressed as a percentage. Okay, so now let's go tackle this. Question number 4. What's my initial value? That's the value that happened first in time. So $55.10. My final value is $54.73. Okay. So now I'm all set to use that formula. I have $54.73 minus $55.10, all divided by the original or initial value of $55.10. And we express that as a percentage. Yeah. So C in this particular case turns out to be a negative number, 0.5%. The negative just means the price dropped. Nothing more complicated than that. If it was a positive number, it means the price went up. Growth not guaranteed to always be a positive number. You kind of, a lot of times you wish it were, but maybe we were talking about costs, and we would be very excited to see costs drop. And that wraps up unit number 2. If you have any questions, please feel free to ask.